Thank Andreas and Francisca for organizing this seminar and for possibility for invitation for and possibility to present the talk here. So my talk will touch two subjects, and the first part of the talk is based on collaboration with Juan Mateus Guierta from Salamanca University, and this part of the talk is also based on related works which we made in collaboration with Francisca Correa, Vit Jakubski, Luis Mineta, Mariana Del Olmo, Adriana Rancibia, and Olaf Lichtenfeld. And in the second part of the talk, I will tell about recent work made in collaboration with Luis Insunza from University of Santiago and Andreas Wipp from Jena University. And the first part of the talk is closely, intimately related, based on some on a PT-symmetry. But the second part of the talk, there are some indications on relation with the PT-symmetry, but at least for me, this relation is not very well clear. So it is rather surprising that the peculiar properties of many classical and quantum systems can be related or can be derived from the properties of a free particle, or from the properties of the simplest possible system. In particular, many of you worked on supersymmetry quantum mechanics and used them, and there are many applications of Darboux transformations, in particular in the context of applications of PT-symmetry in optics. So it is very well known for you that by applying Darboux transformations to free particle, it is possible to generate reflectionless quantum systems. Then, if we use Darboux covariance of Lux pair representation for Korteweg-de Vries equation, we immediately can promote the corresponding potentials of reflectionless quantum systems into solutions of the Korteweg-de Vries equation, of the classical Korteweg-de Vries equation. And from this point of view, any reflectionless system is a kind of snapshot of, in general case, of multi-soliton solution to the Korteweg-de Vries equation. Then, by periodization of reflectionless systems, at least of some of reflectionless systems, it is possible to generate finite gap quantum systems, and they are solutions of stationary equations of the Korteweg-de Vries hierarchy. Again, a Darboux covariance of Lux representation also can be applied to corresponding potentials, and they can be also promoted to the so-called knoidal type solutions of the Korteweg-de Vries equation. The indicated relation between, in particular, reflectionless systems and Korteweg-de Vries equation is very well known, that it is this relation is based on the inverse scattering theory or method, according to which is the spectral deformations of the corresponding multi-soliton Schrödinger potential correspond to evolution in the time parameter of the Korteweg-de Vries equation. Darboux transformations also can be applied to finite gap systems to produce new solutions to the same Korteweg-de Vries and modified Korteweg-de Vries equations. And such systems, corresponding systems, represent soliton defects propagating in asymptotically periodic finite gap background. Then it turns out that with all these mentioned quantum systems, some exotic nonlinear supersymmetric structure can be associated via the same Darboux transformations. And this is, in the simplest case, instead, if we make the minimal supersymmetric extension of a given system, so instead of usual case in which we obtain in such a way n equal to conventional supersymmetry described by a Lie algebraic structure, instead, in this case, we obtain some n equal 4 nonlinear Poincare supersymmetry, which involves Lax-Novikov integrals of stationary equations of the Korteweg-de Vries hierarchy. And in general case, any two reflectionless or any two isospectral or almost isospectral finite gap systems also can be related by two different Darboux-Kram transformations. And this phenomenon is related to the presence of the Lax-Novikov integral in the systems. I will on the one of the next pages, I will explain on what this phenomenon is based. That is the possibility to introduce two Darboux transformations. And extended system is described by four supercharges in the simplest case instead of conventional two supercharges, and the anticommutators of those supercharges produce in general case Hamiltonian or polynomial in the Hamiltonian, but moreover anticommutator of some supercharges also generate Lax-Novikov integrals of the subsystems. So Lax-Novikov integrals represent additional bosonic generators which are higher order differential operators. And it is important that Lax-Novikov integrals always are higher order differential operators of the odd differential order. These integrals play very important role in the corresponding reflectionless or finite gap systems. Namely, they separate left and right moving deformed plane waves of reflectionless systems in the continuous part of their spectra, or left and right moving Bloch states of finite gap systems. And moreover, Lax-Novikov integrals detect all the bound states in the reflectionless systems, or all edge states in the case of the spectrum of finite gap systems. And it is important that in the case of reflectionless systems, a Lax-Novikov integral represents a Darboux-Drest form of the momentum operator of the free particle. So the peculiar properties of the reflectionless systems can be naturally understood again in the light of the corresponding Darboux transformation applied to the free particle. On the other hand, it is very well known also that Korteweg-de Vries equation has rational solutions, but those rational solutions have singularities. And it is also very well known that Calogero-Moser type systems govern the dynamics of moving poles of those rational solutions of the Korteweg-de Vries equation. Such corresponding rational solutions to the Korteweg-de Vries equation can be obtained via appropriate limit procedure from multi-soliton solutions of the same equation, and then by employing Galilean symmetry of the Korteweg-de Vries equation. But on the other hand, such rational solutions can be obtained also directly from the free particle by applying some singular Darboux-Kram transformations. But those singular Darboux-Kram transformations, they should have a very special nature. I will comment on special nature of those transformations in this case. And the simplest case of two-particle Calogero system corresponds to conformal mechanics. Schrödinger symmetry of a free particle reduces, in the case of collinear systems, to SL2R symmetry. And as a result, Lax-Novikov integral is lost in this case. That is, formally, this corresponding operator commutes with the Hamiltonian operator, but Lax-Novikov operator integral, formal integral acting on physical states of the system which satisfy the corresponding boundary conditions, transform those states in the states of the same energy, but which are non-physical states which do not satisfy the necessary boundary conditions. So as a consequence, also exotic supersymmetry is lost. So then the natural question appears whether the nice properties of Lax-Novikov integral can be restored, that is, whether it can be transformed into the true integral of motion, and whether the corresponding supersymmetry, exotic supersymmetric structure can be restored. And the answer is yes to this question, and this can be achieved via the simple PT regularization procedure. So for this, it is necessary to change the real coordinate by shifting it into the pure imaginary direction. And as a result, in this case, the corresponding Lax-Novikov integral will have no singularities on the real axis, and the corresponding Hamiltonian of the obtained system will be PT invariant instead of self-conjugated to be self-conjugated operator. The peculiarity of such PT regularized systems, which can be obtained via the special Darboux transformations, allows to obtain perfectly invisible systems in which transmission coefficient, but not only its absolute value, is equal to 1. And this happens because the corresponding Darboux transformation is based on the eigenstates of the free particle system, which corresponds to zero energy, or on the Jordan states, so-called Jordan states, which correspond to the same zero energy. Another peculiarity of the obtained systems is that each of the systems contains a unique bound state at the very edge of the continuous doubly degenerate part of the spectrum. And also it is possible to observe that the presence of Lax-Novikov integrals in perfectly invisible PT regularized zero-gap quantum systems affects essentially conformal and superconformal symmetries. So Lax-Novikov integral modifies and extends the corresponding conformal symmetry into a nonlinearly extended generalized Schrödinger algebra. And also for the in the extended systems composed from, in the simplest case, from the pairs of the corresponding Darboux generated systems, exotic supersymmetry can be recuperated via this PT regularization procedure. Now I would like to discuss some simple examples. So let us consider the Darboux transformation based on the following shown here seed state. So this wave function is eigenstate of the simplest two-body collinear model with the omitted center of mass degree of freedom. So this is the eigenstate of this Hamiltonian of zero energy. This the first function 1 over xi is physical eigenstate of this Hamiltonian, that is, it is quadratically integrable on the real axis state. And another state is the state of the same zero energy, but it is non-physical. It is not a quadratically integrable system, quadratically integrable wave function. Then we can promote, we can generate via Darboux transformation. We can generate in a usual way. We can first generate the corresponding superpotential, which has the shown here explicit form, and then we obtain two related potentials. One potential corresponds exactly to the simplest Calogero model, and another potential is given by such a potential. Now you see that here they repeated the parameter gamma. Really, parameter gamma is obtained by inclusion dependence, the dependence in this coefficient, the dependence on a time variable. Really, this can be obtained in a regular way by using the mentioned before Darboux covariance of the Lax pair formulation for Korteweg-de Vries equation, or directly it is possible to understand the nature of this parameter. It is the complex valued parameter. It depends linearly on time, and parameter nu is real parameter which is chosen to take values in the indicated interval. This indicated interval guarantees that when parameter of time evolves over all the real lux, the corresponding wave function will not have zeros on the real line, and as a consequence, the corresponding superpotential will be non-singular, and the obtained potential also will be non-singular potential on the real line. And you see when parameter gamma tends to infinity, that is when time parameter of the which corresponds to the evolution parameter of Korteweg-de Vries equation tends to infinity, this potential corresponds to the next term in the Calogero model family of the systems. Now,
can I ask you a question here? Sorry.
Yeah, of course.
Chi only depends on X. So is it correct that you transformed a time-independent Hamiltonian into a time-dependent Hamiltonian?
Yeah. Of course, you see from the explicit form, you can put just t equal to 0, and in this case, the corresponding potential will satisfy the corresponding higher equation in the Korteweg-de Vries hierarchy. But if we introduce such a dependence on time, the corresponding potential which we will obtain, I will show you, will satisfy the complexified Korteweg-de Vries equation. And as I told, really it is possible also to obtain this parameter if we start from the parameter with t equal to 0, and if we use the Darboux covariance of the Lax pair formulation for Korteweg-de Vries equation. I responded you, Andreas. I responded.
Yeah, thank you.
Okay.
Thank you.
Okay, so here it is shown that this non-trivial potential with non-trivial dependence on time, it satisfies the complexified Korteweg-de Vries equation, and its real and imaginary parts satisfy the indicated here system of coupled equations. I would like to note that such complexified form of Cartevec-de Vries equation was in some another context, in some another form, was also investigated or appeared in the works of Andreas and of Carl. Also, Carl Bender also had some works on the complexified form of Cartevec-de Vries equation. So you see here on these two pictures, it is shown the evolution of the real and imaginary parts of the potential V plus. So by a dashed line, it is shown the form of the potential real part of the potential V plus for very big negative value of the time parameter. The continuous form of the real part of this potential corresponds to the time equal to 0, and the dotted form of the potential real part of the potential is shown for very big positive value of the time parameter. And on the right picture, you see the same for the imaginary part of the potential V plus. So you see that by choosing appropriately the parameters in the solution, one can obtain the solutions which of the Cartevec-de Vries equation, complexified Cartevec-de Vries equation, which have a typical nature of the extreme or rock waves. And on this picture, on this page, you see another example which corresponds to the corresponding potential, which almost is a spectral to the next term in the Calogera family of the systems, and the indicated corresponding potential can be promoted to the solutions of the higher order equation of the Cartevec-de Vries hierarchy. And on these pictures, you see again the real and imaginary parts of this more complicated complex potential. Now, I would like to demonstrate the peculiar nature of the supersymmetry which can be associated with such systems. And I would like to demonstrate this by looking at the simplest possible system, supersymmetric system, which can be generated by using such Darboux transformations. But I would like to return and make a very short comment. You see that I constructed the corresponding non-trivial potential by applying Darboux transformation, and which is based on this seed state, which is eigenstate, formal non-physical eigenstate of this shown Calogera model Hamiltonian. But really, it is possible also to generate this potential by using as the seed states the zero energy eigenstate of non-physical eigenstate of the free particle, and also Jordan states of the free particle, which correspond to zero energy. Jordan states means that the corresponding wave functions which correspond to zero energy, they do not annihilated by the Hamiltonian, but they are annihilated by the corresponding higher orders of the Hamiltonian operator. So in the simplest case, let us consider the composed system which is constructed from the free particle Hamiltonian and from the PT regularized simplest Calogera two-particle Calogera model Hamiltonian. So in this case, Hamiltonian, one can construct two supercharges, two pairs of metric supercharges, which commute with Hamiltonian, and one pair of supercharges is constructed by using the following Darboux intertwining or Darboux generating operator, which is nothing else as this operator annihilates the function psi, which is non-physical eigenstate of zero value of the free particle. But another pair of supercharges is constructed in terms of the second order intertwining operators, and the possibility to have this second order intertwining operators appears from the, as I mentioned before, of the special nature of this operator P1 alpha, which is the Lax-Novikov integral for the subsystem, for the upper subsystem. And you see that it is the Darboux dressed form of the free particle momentum operator. And you see that this operator can be interpreted as D1 multiplied by the second order operator, or it can be interpreted as D1 multiplied by P0. This is the second order operator multiplied by the first order intertwining operator. So we have two possibilities to factorize the Lax-Novikov integral in terms of the corresponding Darboux intertwining operators. And as a consequence, we have a possibility to construct two different pairs of different differential order supercharges. And it is important that each time Lax-Novikov integral of motion is, as I mentioned before, is the differential operator of the odd differential order. And it means that always, if you have a similar superextended system, one pair of the supercharges will be matrix differential operators of the even differential order, and another pair of supercharges will be differential matrix operator of the odd differential order. And it is interesting, as I told before, this Lax-Novikov integral, it separates the deformed plane wave eigenstates of this upper Hamiltonian operator, and its kernel includes the zero energy, physical zero energy eigenstate of the system, and also it includes these non-physical states. Psi is non-physical zero energy eigenstate of the free particle, and this is the psi cube is Jordan state of the free particle corresponding to zero energy. Square of the free particle Hamilton operator annihilates this state. Or if you apply to these states the same PT-regularized Calogera Hamiltonian operator, these non-physical states will be transformed into the zero energy eigenstate of the PT-regularized Calogera subsystem. In principle, one can introduce also another very important comment, that you see that supercharges anticommute for linear supercharges anticommute for Hamiltonian, second order supercharges anticommute for the second order, the anticommutator second order in Hamiltonian, and the corresponding anticommutator of the supercharges of the indicated different nature, they produce the this bosonic non-trivial integral of motion for the extended system. And this bosonic integral, in the case of the system, which is characterized by unbroken supersymmetry, it is central charge of superalgebra. It commutes with Hamiltonian and with all the supercharges. But in principle, one can construct another operator, bosonic operator, and this another bosonic operator will transform mutually these two pairs of supercharges of different nature. And here it is shown another example of superextended system, which is completely which is corresponds to completely isospectral. The corresponding superextended system is constructed from the completely isospectral PT-regularized Calogera model Hamiltonians, and the corresponding PT regularization parameters are different. And it turns out that these two systems can be intertwined by intertwining operators of two different kinds. One intertwining operator is the second order differential operator, and effectively this operator intertwines the indicated two Hamiltonians via the virtual free particle system. That is, the first factor will transform commuting with the Hamiltonian will produce a free particle Hamiltonian, and then applying action by the second factor, we produce the partner Hamiltonian. But it is important that besides the second order intertwining operators, this system is characterized also by the presence of the first order intertwining Darboux intertwining operator, which has the shown here form, and the corresponding superpotential is indicated here. Xi1 and Xi2 are x plus I alpha 1 and x plus I alpha 2. So these first order differential operators, they directly intertwine these two Hamiltonians of two subsystems. But it is important that the second order that this first order intertwiners, their product is not the Hamiltonian but the shifted Hamiltonian, and the shifting constant depends on the difference of the regularization parameters alpha 1 and alpha 2. And as a consequence, one can show that in this case, the corresponding superextended system is characterized by the partially broken supersymmetry. In this case, the first order supercharges do not annihilate a pair of zero energy eigenstates of the system. And it is also this partially broken nature of exotic supersymmetry is also reflected in the structure of the corresponding superalgebra. In this case, the form of superalgebra has more complicated form. It is possible to show that in this case L1 here I did not show, but one can show that L1 in this case is not central charge of the corresponding superalgebra. And I would like to make a short comment. If we try to extend the supersymmetric structure by taking into account the conformal symmetry of the free particle system, which appears here as a subsystem, or conformal mechanics, conformal models, they are also characterized by the conformal symmetry, which is generated by Hamiltonian and by dilatation, corresponding dilatation operator, and corresponding corresponding generator of special conformal transformations. But in the case of PT regularized Calogera systems, the corresponding dilatation and special conformal transformation generators have more complicated form in comparison with the free particle case, but they can be constructed explicitly. And it turns out that if we extend the discussed before Poincare supersymmetry by generators of conformal symmetry, and if we extend the corresponding set of generators by Lax integral, matrix integral, as a result, in the system there will appear new non-trivial integrals of motion, which are shown here. These are the corresponding diagonal non-trivial bosonic integrals, which depend explicitly on time. And the set of odd integrals also will be extended. And the peculiarity in the case of the shown first superextended system is that in this case, for such system, we have the same number of even and odd generators of corresponding superalgebra. And a peculiarity in that case is that all the bosonic and fermionic integrals, they are eigenstates of the dilatation operator multiplied by minus I with certain eigenvalues. And this is and as a result, one can show that the inclusion of conformal symmetry in the first superextended example produce some kind of extended nonlinear version of conformal superalgebra, which includes OSP22 as Lie superalgebra in the form of sub superalgebra. But it turns out that in the case, if you consider another model, demonstrated superextended model, the structure of supersymmetry will be much more complicated. In that case, it turns out that no fermionic integrals are eigenstates in the sense of the dilatation operator, and OSP22 superconformal algebra is not contained in that case as sub-superalgebra in the corresponding nonlinearly extended conformal superalgebra. It is. I would like to make a short comment that it turns out that some of the shown PT regularized conformal systems appear in the context of Liouville and SU3 conformal Toda systems. They appear as their Hamiltonian operators appear as differential operators that control stability properties of the corresponding King-type solutions in the indicated field systems. And as I already mentioned, in the described construction, Jordan states corresponding to zero energy play essential role. And we shall see that in another construction to the discussion which now I will pass over, the Jordan states also play the fundamental role. So all the picture which I have discussed can be summarized in this symbolic picture. So starting from free particle system, applying the corresponding Darboux transformations, we can generate reflectionless systems or finite gap systems, or we can also generate zero gap perfectly invisible quantum systems. if we apply PT regularization and by using the corresponding covariance of Lax pair formulation of Cartevec de Vries equation under Darboux-Krahn transformations, the corresponding stationary the corresponding systems with corresponding stationary potentials, which are solutions of the corresponding higher order equations in Cartevec de Vries hierarchy, can be promoted to the corresponding to the solutions of the Cartevec de Vries equation. And in the class of the systems which I discussed, which corresponds to zero gap, perfectly invisible quantum systems, essential role is played by Lax-Novikov integral, which represents the Darboux-Dressed form of the momentum operator of the free particle. So we saw that many interesting systems can be related, physically interesting systems can be related to free particle. But we have another elementary and very fundamental system, which corresponds to the quantum harmonic oscillator. So rather natural question which can appear here, whether it would be possible to generate a quantum harmonic oscillator starting from the same, in the simplest case, one-dimensional free particle system. And a priori it is clear that it is not possible to relate these two systems by Darboux-Krahn transformations because Darboux generators are differential operators of the finite differential order, but free particle and quantum harmonic oscillator have radically different spectral properties, and so they cannot be mapped one to another by applying intertwining operators of the finite differential order. And now I would like to show you how that really these two systems also can be related, and then the construction can be generalized for some other systems, and it can be the corresponding construction is based on the so-called conformal bridge transformation, which is based on the another fundamental property of free particle and quantum harmonic oscillator, that both systems, quantum harmonic oscillator and free particle, both of them are characterized by conformal symmetry, but which is realized in some different forms. That is, I mean that in the case of free particle, the role of the Hamiltonian is played by this operator, which has the nature of non-local generator of SO to1 algebra or isomorphical to it SL2 algebra, while the quantum Hamiltonian of oscillator corresponds to the compact generator of the same algebra. So the construction that I will discuss really corresponds to different forms of dynamics according to Dirac. Dirac discussed different forms of dynamics. According to him, if we have the system which is characterized by some symmetry, we can generate dynamics using one or another on some another generator of the same symmetry algebra. But peculiarity in this case that the symmetry which I will employ, that is conformal symmetry, it is generated by the so-called dynamical integrals of motion. I mean that K and D generator of special conformal transformations and of dilatations, they do not commute with the Hamiltonian, but they can simply be promoted into integrals by including some explicitly depending on time terms, corresponding operator terms. So if we pass to this combination of the generators, we can represent algebra maybe in more familiar form for SL2 conformal algebra. Now let us define the following non-unitary operator shown here. That is, it is constructed in terms of exponentiation of the generators of the conformal symmetry of the free particle. But it is important that there are 2 points. First of all, you see that these generators H0 and K, they enter into this operator. The corresponding parameters are pure complex. So this operator is non-unitary. And another characteristic is that this is the non-local operator, since this is the operator which includes which includes derivatives of arbitrary high order. In terms of the introduced G generators denoted here by G, this introduced non-unitary operator can be represented in such a more symmetric form. Now, what is the nature? What is the job made by this operator? You see that this operator, when it is applied to X and P operators of the free particle and to corresponding the linear combinations which correspond to creation and annihilation operators of for the harmonic quantum harmonic oscillator, they are transformed in the indicated here form. X is transformed into the increasing or creation operator. P is transformed into the decreasing operator, and the fourth order of this operator makes the indicated here job. So you see that the fourth order of the introduced operator has the nature of the spatial reflection operator. It changes the signs of X and P. And so it is the operator sigma has the nature of the root of order 4 of order 8 from the identity operator. When this operator, on the other hand, when this operator acts on the generators of SL2 are algebra, that you see that it transforms generators into generators, but it transforms generator of a compact nature into generator of non-compact nature, and vice versa. And also in this transformation there appears the square root of -1. So really, since the corresponding transformation is similarity transformation, it does not change the form of the corresponding SL2 algebra. So really, sigma generates non-unitary automorphism of SL2 conformal algebra. And when it acts on the generators of SL2 algebra, really one can see that the square of this operator is the rotation for angle pi about the axis which corresponds to G1 non-compact G1 generator of SL2 algebra. But another interesting peculiarity of this operator is that it is PT invariant operator. That is, if we introduce the time reflection operator, which anti-commutes with square root of -1, it is easily to check that this operator is PT generator of the conformal bridge transformation is PT invariant operator. So you see, as I mentioned before, this operator acting on the dilatation operator of the free particle, it transforms and multiplied by, it is important, multiplied by I, it transforms it into the Hamiltonian operator of the quantum harmonic oscillator. So this similarity, this generator of conformal bridge transformation really corresponds to the change of dynamics in the sense of Dirac. Now, it is interesting to make the following observation. You see that one can consider the classical analog and corresponding transformations of a sigma operator. It generates complex canonical transformations in the phase space. And in particular, X variable is transformed in classical analog of the creation operator of the quantum harmonic oscillator. And the transformed P with factor minus I is transformed into the annihilation operator of the quantum harmonic oscillator. So if we apply the complex conjugation to transform the X variable, it transforms into A plus conjugated is A minus. So it corresponds to P multiplied by I. So at the quantum level, we can pass over from the coordinate representation to representation in which the coordinate operator acts as the operator multiplication by some complex variable z, while momentum operator acts as the differentiation operator in this complex variable. And then if we replace the initial standard definition of the scalar product, which corresponds to integration over a real line, we for the scalar product, which corresponds to the Fogg-Bergman representation, we see that the corresponding A plus and A minus operators, which are given by multiplication differentiation in the complex variable Z, they are mutually complex, hermitially conjugated with respect to this Fogg scalar product. And this corresponds to the observation which I indicated, which we have at the classical level. And it is interesting that in this representation, the transformed dilatation operator, which corresponds to the Hamiltonian of harmonic oscillator, takes such a form. And here you see the corresponding transformed Hamiltonian operator of the free particle and generate special conformal transformations. And you see that formally these operators have exactly the form of the corresponding operators for free particle, but with x changed for z and d, and minus d over dx changed for d over dz. So the change of the scalar product transmute the unitary similarity transformation into the unitary transformation from the coordinate to the holomorphic representation for the Heisenberg algebra. And this corresponds exactly to the Newman-Stone theorem, which says that representation of the Heisenberg algebra is unique up to the corresponding unitary transformation. So I have discussed until the moment the action of the constructed, introduced operator on the generators of conformal algebra. So what is the job made by this operator when we apply it to different states of the free particle? So if we apply this operator to Jordan states of the free particle, which correspond to zero energy of the Hamiltonian of free particles, that is, these wave functions are annihilated by the corresponding degrees of the Hamiltonian operator of the free particle. But and the first two states in this family correspond to physical and non-physical eigenstates of the free particle of the same zero energy. But on the other hand, these functions are formal eigenstates of the dilatation operator multiplied by I. And they are eigenstates, formal eigenstates of the shown here eigenvalues. So after application of the operator S to these states, we obtain up to normalization constants, we exactly produce eigenstates of the quantum harmonic oscillator of the corresponding energy eigenvalues in correspondence with the job made by this operator when it acts on the generators of conformal algebra of the free particle. It transforms dilatation operator multiplied by I into the operator of Hamilton operator of the quantum harmonic oscillator. On the other hand, if you apply this operator, the same operator, to plane waves eigenstates of the free particle, they are transformed into coherent states of the quantum harmonic oscillator. And another interesting class of the systems which we can consider for free particle correspond to Gaussian wave packet, which we can construct using the superposition of the eigenstates of the free particle. And it is interesting that Gaussian wave packets, by applying this operator sigma, are transformed into squeezed states of the quantum harmonic oscillator. And in conclusion, I will mention the further generalizations, possible generalizations of the conformal bridge, of the discussed conformal bridge transformation. So if we apply it, so you see that the same construction can be applied to relate asymptotically, some asymptotically free system characterized by conformal symmetry and the related to it harmonically trapped system. So that is which includes quadratic potential term. So in this, so it is important that the initial system and transformed system are characterized by the presence of the conformal symmetry. So in this way, the analog of corresponding analog of conformal bridge transformation can be applied and to transform conformal mechanics systems, which really correspond to the simplest two-particle Calogero model with omitted center of mass. The corresponding conformal mechanics system will be transformed into the corresponding conformal mechanics model of discussed by Del Faro, Fubini, Furlan, and the interest which reappeared recently in the context of some black hole solutions and supersymmetry for the corresponding black hole related to black hole systems. Another interesting application that applying the same conformal bridge transformation, but in some a little bit modified form to two-dimensional free particle system. One can relate two-dimensional free particle system to the Landau problem in the plane. Another application which was realized corresponds to the map between conformal mechanics and the Alfaro Fubini Furlan model in a three-dimensional monopole background. And finally, this is the work in preparation. It turns out that free particle system also can be related to the quantum harmonic oscillator in the background of the cosmic string. So thank you for your attention.
So maybe we can unmute ourselves in order to thanks Mikhail. Thank you very much. So there are any questions?
I have a question related to the KDV system. Yeah, and you speak about the supersymmetric KDV systems. They are, if you start from another formulation going back, I think, to Mathieu in the 80s, they are supersymmetric extensions of the KDV models properly involving fermionic fields. Do you have an idea how this relates to your formulation in some sense? I mean, it doesn't directly, but it could be extended to that. So one would have two notions of supersymmetry in a way.
Yeah, Andreas, if I understand correctly, you say about another system. That is,
yes, that's another system.
Supersymmetric extension of the Korteweg-de-Vries equation.
That's right.
Yeah, we did not try to see in that direction. So I cannot say whether it is possible to relate somehow our construction with that mentioned by you supersymmetric extension of Korteweg-de-Vries equation. I don't know, so I cannot comment on this point.
Because if one did this, one would have two notions of supersymmetry, which are kind of different.
Yeah, understand, yes. But I don't know whether it is possible to relate this to a class of systems or not. I don't know.
Right, thank you.
Thank you.
May I ask a question?
Yes, go ahead, Olaf.
Yeah, we have the nonlinear extensions of the superalgebras. But it made me thinking of the most general mechanical superalgebra D2,1 alpha, which depends on the parameter alpha. It has some of the ones you mentioned as special limits. Does this algebra occur, or some nonlinear generalization occur somewhere in your game, or is it impossible to include that?
Olaf, I'm sorry. Can you turn off your video and ask the question again, because
it is impossible to understand the question. Sorry.
Okay, I don't know.
Okay.
So can you understand me now? Is it better?
Yeah.
Okay. Okay. So you had this nonlinear super extension of superalgebras.
Yeah.
Thinking of this most general mechanical superalgebra D2,1 alpha, which depends on the parameter alpha. Does this occur anywhere, or some nonlinear extension of that occur anywhere in your game, or is that excluded for some reason?
Yeah, really, Olaf, this is a very interesting question. That is really, you see that I mentioned at the end of the talk, I mentioned this generalization, which corresponds to the cosmic string background. So really, the interest to look that class of systems exactly corresponds to your question. That is, I suspected initially that in such a way there should appear in some natural way this exceptional D2,1 alpha superalgebra which you mentioned. But in order, so that was the motivation to investigate the indicated systems. But in order to ask your question, in order to respond to your question, it is necessary to investigate. This is one of the problems we plan to consider in the nearest future. It is necessary to consider the extension of the conformal bridge transformation to the case of the super extended case. That is, at least in the case of conformal bridge transformation, till the moment we did not apply in a regular way that transformation to the. We did not consider that transformation in the context, in the regular way, in the context of supersymmetry. But on the other hand, it is possible to say that you know that in the case of the monopole background, magnetic monopole background in 3 dimensions, you know our my first work with Andreas Wipp, where we showed that for special values of the coupling constant in the conformal term, when coupling constant is related to the charge, the product of charge monopole of magnetic and electric charges. In that case, in that case, the system has some hidden symmetry, and one can consider the supersymmetric extension of the corresponding system. And you know that in that direction, one can reproduce the exceptional D12 alpha superalgebra, but for some very restricted finite set of values of the parameter alpha. But I suspect that in particular, as I told you, having in mind this conical background, I suspect that it is possible. As I told you, that was motivation to look at that system. I suspect that it is possible to extend the construction to include somehow naturally the indicated exceptional superalgebra.
Okay.
So thank you. The question is very interesting, and really we are thinking in that direction.
Maybe just one comment. You may have seen that Anton Galajinsky has recently shown in various papers that it's possible when you have a superparticle, a mechanical realization of superalgebra, that you can always generalize it to the E2 1, alpha realization. So it is possible to do this in a canonical fashion. Maybe you have a look at that.
Okay, and this works of which year?
Galajinsky.
Yeah, of Anton, but of which year?
Oh, just recently, the last 2-3 years. Very new.
Okay, I will check. But also you had also had some work on the same subject.
Indeed, yes.
Written in collaboration with Anton. Okay, I will really that work, your work with Anton, as I mentioned, was the motivation to look at least for conformal bridge transformation in that context. Thank you.
Okay.
So, thank you very much. Is anyone else with a question?
Can I have a question?
Yes, sure.
Hello, Mikhail. Hello, everybody.
Hello.
Thank you for a very nice talk. In the first part of it, you were speaking about Calogero model that was obtained by Darboux transformation from the free particle system.
Yeah.
And well, you used these zero energy states, and you got the Calogero system and also some very complex algebra or superalgebra. My question is, what happens if you use states of different energy, not of zero energy? I can imagine that you don't get a Calogero model, but is there some similar structure of superalgebra in the new system?
Thank you. With 2 points related to your questions. First of all, as you know perfectly, and I mentioned without indicating the explicit list of the articles, really we, for my work made in collaboration with Juan, our work was based on our previous work with you and with Francisco, where exactly we considered exactly the systems you mentioned, and when we exactly used as seed states for Darboux transformation some states corresponding to other values of energy. In such a way, in particular, as you know perfectly, it is possible to introduce some bound states, in particular if you start from free particle bound states, the analogs of Wigner-Neumann states, which are bound states inside the continuous spectrum. And you know also the corresponding works of other authors which applied a similar transformation in the context of some optical systems. But the peculiar, yes, it is possible to use, and it is possible also to use the states which correspond to other values of energy. It is possible to produce some other interesting, physically interesting systems. But the point, the peculiarity of the states and eigenstates and Jordan states of zero energy is that these states you see that the zero energy states, they reflect the scale symmetry of the free particle system in particular. And because of that, the systems which we obtain, they are characterized by very special properties. That is, in particular, those systems have the unique bound state at the very edge of the continuous part of the spectrum. And these states, corresponding states, are of zero energy. And as there is some work of Francisca with Andreas, they considered some another class of systems, but in some related context. And okay, and there, we have some work in progress on that subject. Really, the use of zero energy eigenstates and Jordan states as seed states for Darboux transformation, the use of these states is also very interesting from the point of view of the same Korteweg-de Vries equation. It turns out that, in particular, if we consider the integral for Korteweg-de Vries equation, which corresponds to the energy of the Korteweg-de Vries equation, the usage of such, the employment of such seed states does not change the value of the energy of the corresponding associated Korteweg-de Vries, deformed Korteweg-de Vries, complexified Korteweg-de Vries field system. So the zero energy, the usage of zero energy eigenstates and Jordan states reflects very peculiar properties of exactly of this energy value. As the any eigenstate or Jordan state related to different from zero energy, the corresponding stationary Schrödinger equation is not then scale invariant. So this this transformation use these very peculiar properties of such states.
Yeah. Okay. Thank you. Thank you very much.
Thank you. I don't know if there is someone else with a last question. Seems not. So let us thank again, Mikhail. Thank you very much, Mikhail, for the nice talk.
Thank you, everybody, for the attention and interesting questions.
So thank you very much. And Mikhail, may we ask you the slides in order to post it in the website?
Okay.
So
see you to everybody.
See you next time.
Bye-bye.
Bye-bye.
Bye.